Okay, I'm going to get this just take a look here. This is a small group for this time frame. And go ahead and use yourself fold the paper in thirds with this and make yourself a little name tag, because that's all I'm going to keep attendance each time when we do this. So those of you that have your cards and you can plug it in and you know that you guys have been. Whoever knows that don't probably doesn't have. Just a second here. Do that. Put what you normally like to normally go by in terms of especially this meeting. Because then I realized initially that it's also fine. Okay, so I don't see anybody's going to join us at 8 o'clock, but just so you guys know, and just in terms of like online, team streaming people. Can I work on a computer? As long as you do it very quietly. What we're going to, I'm still going to record this session to see how it, see if you get some good sound. I've added a mic now, and that will help me know, although that mic is probably not as good as the one I'm going to try and get. At least it will help us know if we are on the right track with everything and get something that's effective. Okay? And are you emailing me about the mic, the issue watching the recording?
Yeah, I can't remember
the link.
like when I click on, like both of them, when I click on the link, the week one, the screen turns gray. Week two, it's like I click on it, and there's like this little like white thing at the bottom that says the link again. But then when I try to click on that, it just like goes away and nothing says.
Okay, so the second link should take you to, for week 2 should take you to the Blackboard Collaborate thing. So that's something that may be an issue with the Blackboard Collaborate system. So contact the support. And YouTube one, just copy it and paste it into a new window, if that works. Okay, and maybe do that same thing with the other one, copy and paste it into a new window, and see if that works. And then I'll work on making sure that the double check that on the link and make sure that maybe putting in any rules don't realize that it's appropriate. That's good. All right, so that should, if you copy and paste it, it should get you there. All right, so we're going to talk about rational and irrational numbers today, and one of the things that you need to know and understand about this is that today we're going to kind of be doing a more direct instruction lesson because we got a lot of kind of circulated kind of things today. Most of the time when you come in, we're going to be actually be a lot more engaged in things and really building ideas, and then then you can go back into the lesson and do the lessons and kind of understand what they're talking about, and then add to your notes and that kind of stuff. Okay. When you're here, if you're taking your pointer notes while you're here, then I will just automatically go put 10 points into here. It's hopefully for the end of the day, but I have a list of who's here, and so I can see what you're doing with your notes and stuff. So that's kind of the benefit here is 4 pinpoints because you're here and making sure that you're getting what you need and in the notes and I can see that you're doing it and then you have to worry about turning that down, put it in Dropbox and all that kind of stuff. You're taken care of and you have it then for yourself for tests and stuff. You guys have to turn it in to me. So that's the first thing. And then the other thing, the next thing is, so I put on here is connect a lot. The next thing is that you need to know is that we have a test tomorrow. Okay, the test is going to be over everything that you have gone through with me. Now, that if you go through the review section, you might have noticed that there are some things in the review section that aren't on that we haven't talked about. Won't be those things won't be on the test. So don't worry, just worry about those sections that we talked about. All right. So that's the next thing you need to know. After that. We have our essential question, and I'm going to do the essential question. I'm going to add to this, and that essential question is going to be. I forgot to put it in there. I'll put it on. I mean, what's the difference between a rational and an irrational number? Okay. So let's get that copy down into your notes. And remember, we still want to do Cornell style notes. So you got to make sure your name's at the top, put your notes in the upper second corner or so, and then the essential questions at the very top, and then you start your notes with the third line. Okay. So before we move on, what do you guys know about rational and irrational numbers? Anything? It's okay if you don't know anything, but if you know something, let's share out what that might be.
Is rational like when there's a fraction that's like 1 3/4, and then irrational would be like 7 3/4?
Actually, a rational number does have to do with fractions, and irrational does have to do with fractions. Okay, but not quite. Okay, so you're talking about like a proper fraction, a mixed number versus an improper fraction, and so those are actually the words that are there. And actually, both of those examples would be rational numbers. So when you have like something that's written in fraction form or mixed number type form, which is still a fraction, okay, versus like the improper fraction, those are both rational numbers. Okay. Any other thoughts? Okay, so the next slide actually is going to talk about some of the vocabulary words that we're talking about. And so we've got something called terminating decimals, non-terminating decimals. rational numbers, irrational numbers, and radical sign and radicand. So kind of put these down and leave a space so you can put the definitions as we go along. We have to come back and note and put those in. But leave a little space to write down that definition, or put it off, put the vocabulary word in your top left-hand column, so you leave space to write your definition right. So the first one is a terminating decimal. What do you guys think that means? What does the word terminating mean? Yeah, okay, so it just stops. So like, if you put 0.4, that would be a terminating decimal because it stops. It doesn't, right? There's only one place value, or 0.75 would be a terminating decimal because it stops. What would be an example of a non-terminating decimal? Okay.
3.3333.
Yeah, that's 0.33333 continuing on. It never stopping is a non-terminating decimal. Or a 0.45454545, right? Okay. So we need to know the difference between that. But you can also have non-terminating decimals that don't repeat. Okay. So you have non-terminating decimals that repeat and some that don't repeat. Right? And so that's the thing that's going to be the difference, help us find that difference between a rational number and an irrational number. Okay? So a rational number is a number that can be written as a fraction. Okay? So like we know that 0.333 repeating is actually what fraction? You guys remember? Yes, it's actually 1/3. So 0.33333 repeating would be a rational number because it can be written as a fraction. Okay? And actually like 0.45454545, we're going to find out today as we work through some stuff, also can be written as a fraction. So it would be a rational number. Okay? So again, rational numbers are numbers, or any number that can be written as a fraction. Okay? The irrational, and that includes terminating decimals, because like 0.4 is 4/10, right? It includes non-terminating decimals that repeat. Okay? So the rational numbers are include terminating decimals and non-terminating decimals that repeat. So the irrational numbers, what do you think those would be now that we know that a rational number is?
A number that can't be written as a fraction.
Okay, it can't be written as a fraction, so what would that look like, do you think? Like pi. Yeah, it doesn't repeat. It goes on and on forever, but then it doesn't repeat, right? Mm-hmm. Okay. And there's other numbers that we're going to deal with today that you'll find are irrational numbers that go on and on forever but don't repeat, such as pi. Okay. So irrational numbers cannot be written as a fraction. They usually are non-terminating. They can be written as non-terminating decimals, or something that will create a non-terminating decimal that does not repeat. Okay. So I'll give you a second or two to kind of jot those thoughts down. Because I know we talked about a lot of things, but you're trying to write these all down. And as you kind of wrapping up your thoughts on this, the reason I started with this is because everything we're going to deal with today is going to go back to these definitions. Okay? So that's why they're so important, because it's going to help us make decisions on different things. Now, radical sign, what do you guys think that means? Any thoughts? The radical sign is this. Is that called, what the meaning for that? That's also the square root sign. Okay, you guys know what square root means? Okay, we're going to talk about that today. Do you know what squaring a number means?
Yes.
What does squaring a number mean?
It's like a number squared would be like 3 and a little 2 in between.
Okay, so it's 3 times 3, because
Yeah.
there's 2 3's, and we write 3, a little 2.
Mm-hmm.
And the square root is actually doing the opposite of that. So 3 squared is 9. Square root of 9 would be 3, because 3 times 3 makes 9.
Oh, so we divided. Okay.
But it's not divide, it's not quite divide,
Yeah.
but it's like multiply and divide, right? You square something, you have an opposite of that square root in. Yeah. Okay? So the radical sign is this is the square root sign, it's also called the radical sign. And then the radicand is the number that goes underneath it.
Yeah.
Okay? No, because I'm going to get, I finished doing it now, so I'm just going to take note that you did it now, and I would automatically go for this once right then on the computer. Okay? So, if we have to convert 4/11 to decimal, what do you think we get? Try it. Go ahead and try it quickly. Converting 4/11 to decimal.
Yeah.
Okay. Is it going to continue?
Yeah.
Okay. So when you remember when you convert to fraction to decimal, you divide, and it would be 4 divided by 11, and so the 4 goes underneath the division sign, and the 11 goes on the outside. As you divide it out, you get 0.363636 repeating. Okay, so we have a repeating decimal with that, and that's actually going to happen for anything with 11. You're going to get a repeating decimal with 2 digits. And with the 4, it's 3636. So you suppose the 3 is going to, if it's 3 11, what do you suppose that might be? Not quite. 2, 36, 3636. The 3 and the 6 makes 9. So 2. That's just 2 7.
Oh, okay.
Okay. What do you think the 2 is going to be? The 2 11. Probably, yeah. There's a pattern with some of these things like that. If I had a 49, that would also be a repeating decimal, but it actually happens to only have one decimal repeat. So we're actually getting the idea that repeating decimal. So let's go to the next slide. Now, what I put up here is I went ahead and put up the problem, And I'm asking you to take a repeat decimal and write it as a fraction. Now, what I did is I said, here's the steps that Jacob used to solve this problem. So I want you guys to sit and talk for a little bit about what is it that he did to solve the problem, and why do you think he did that? So I'm giving you the steps. I want you to think about why those are the steps and what he did. Because we're going to learn how to change a repeating decimal to a fraction. So we haven't learned that before, I don't think. So go ahead and look at that, think about it, and talk about it. So you can talk to each other. It might help to start by what he did at each step, and figure out what he did at each step, and then go back and think about why. You ready? Okay. So you guys have the same boat?
I kind of understand it.
You can understand it? So talk with each other about it. What do you understand about the first step?
I understand that step one is the original equation, like x equals 0.3 repeating.
Okay, so there was not an original equation, so he created an equation and said x equals that, didn't he?
Mm-hmm.
Okay.
And so then he multiplied each side by 10. So why would he do that? So he'd have a number to work with. It's with a value.
Okay. Okay. So he multiplied by 10. Why did he choose 10 instead of some other number? It is an easy number to work with. What does it cost Calvin? Look at what happened here, and then look what happened just right here. Ignore this part right here right now, like up to that point. Oh, so if I'm multiplying by 10 or 100 or 1,000, it moves a decimal point.
Mm-hmm.
Okay? And he asked it to move one place. Why do you think he only wanted it to move one place?
Because it's easier. If he had done 1,000, he probably still would have been able to complete the problem, but it would have been harder.
Okay, that's true. But why do you think he just that's true? But there was a reason they chose 10.
So you mentioned easier fraction.
We'll think about it. So let's think about that. So keep that question in your mind, because I'm going to have another problem up there in a couple of minutes, and that might help me answer that question. Okay. So he multiplied both sides by 10, and he got 3 points, then the 3 repeating, right? Then what did he do here?
He subtracted the equation he had come up with.
Okay, good. And one of the things we know is if we add equal things or subtract equal things from equal things, we still get 2 things that are equal. So if I have 10x minus x, I get 9x. What happens here?
If you only take away 0.3, then you end up with like 3.
So what happens? Do you guys like working with that repeating decimal thing?
Oh, if he had 0.3 repeating and you took away the 0.3 repeating, then it no longer repeats itself.
Yeah. And now we can work with it, can't we?
Mm-hmm.
Right? Okay? So now then what did you do? Now he got this, 9x equals 3.
And you divided it by 9.
Yeah, and then he just solved for x, didn't he?
Mm-hmm.
Okay, so it divided both sides by 9.
Okay.
We've done x equals 1/3, which we knew already, because we know if 0.33 repeating is 1/3. We kind of learned that along the way, right? That's why I chose this one to start with.
I think he multiplied it by 10 because he needed enough like numbers, like values, so that he could subtract the original equation and still have like not negative numbers.
Okay, you didn't want negative numbers. Okay, that could be true. Okay, so keep that in mind, let's think about it. So basically, let's just kind of quickly review what he did. He wrote it as an equation, x equals. He multiplied both sides by 10, so that here, we got this. And I'm not going to give away why he did it. Here, we're going to figure out, we need to think about why did he do that, because that's important. Then he subtracted the original equation from the new equation. Then he just solved for the variable. Okay, so let's look at the next one. And see if we can figure out why he multiplied by what he multiplied. So this time Hannah is doing the problem. And she's got one that's got two numbers that are repeating. So did she basically do the same steps?
I get it. I get it.
Did
I
she
get
basically
it.
do the same steps
Mhm.
as what Jacob did? Okay, so what are the steps she did?
She first wrote down, like, she needed to solve for 5400 repeating as a fraction. And that means that it would just be like 0.545454, like over and over again.
Mm-hmm.
And since that's two places, she needed to move it two place values, so she'd have enough, like, because the other one was just 0.3, so we only have to move it one value. But this one was two repeats, so we had to move it two values.
Does that make sense? Yeah. Okay, this one there's two numbers repeating, so she decided to multiply by 100. Why?
And she can move it over two place values instead of one.
Yeah, because it doesn't point then those two places instead of one.
So then when
Okay.
she takes away the original 54 repeating, she's left with the whole number.
Yeah, because the idea in the first one is that one problem before was we needed to get rid of the repeating decimals, right? So we could work with it. And so that's the idea here. We're trying to get rid of that repeating decimal so we can work with it. Excellent. And in order to do that, since we've got two numbers repeating, we had to multiply by 100. What happens if it was three numbers repeating?
You multiply by 1,000.
Mm-hmm. Okay? Make sense? All right? And then she just followed the rest. She just subtracted her original one, so we can get rid of the repeating. Get this. We're to solve it. Then we just simplify it down and we get this 11. Okay? Make sense? All right? So, let's look at one more here. Now I didn't give it to you. Guess what you get to do now? You get to do it, and we're going to talk about, we should get those written steps down for you guys in your notes. Okay, so just if you subtract it normally, if you have one decimal point, make sure you learn the decimal point. Because all we're worried about is this part.
So then there's the 6.
Yeah, right. Yeah, but that, this will just subtract like you normally would in this number. That's one. Yeah, that was the tricky part about this one. When you multiply this by 1,000, what did you get? You're perfect. Put the 1,000 in. But storing that from that. What did we subtract before? We subtracted this, right? The whole thing. So when you subtract, what do you have to do? No, not quite. Once you get 1,000, I can really want to know it. You got it. So what happens here? If you multiply by 10, it has to be different one. There's one place, right? And if you multiply by 100, what happens? So if you multiply by 1,000, 3 times. So the circle should be, and what should be after? If it's repeat, what comes after this? That's the judgment. Okay, so now you can subtract the 6 points and go for it. It's going to be this fraction. It can be a mixed number, a fraction, but actually, no, it's not. If you subtract that, this is like the next here, right? That equals out. So you subtract the extra here, so what number should be here? This is the fraction of the This right here should be x equals that. I'm subtracting this also, so 1,000 minus x would be no. If I have 5 x's and I take one of them away, I get 4 what? 4 x's. So if I have 1,000 x's and I take them away, I get x's, right? Okay. This is still, this one didn't change. So this. So I have to line my decimal point up, right? And then stop. Okay? Okay? So let's talk about what you guys did. Just finishing it up, but let's talk about what you did. And see if we can figure out what the steps are and write the steps down that we did. So what was the first step that you did? Before you ever multiplied or anything like that, what did you do?
You added x to the equation by writing it as x equals 6,154,000 repetitive.
You wrote it as an equation and set it equal to x, right?
Mm-hmm.
Okay? Or if I set it equal to x. So let's write that down. Write it as an equation. That's your first step, right? Small bit. Okay? So, I'm sorry, I thought that thing didn't pop up so I could change the size of the font. So you write it as an equation and set it equal to x. Okay? Then what did you do? What do you mean by that? Okay. So the next thing you did was you
Multiply each side by 1,000.
okay, multiply each side by 1,000. Okay. So you should have something like this on your paper. And if you want to go straight to the, why did you multiply by 1,000?
Because there were there were 30 repeating decimals.
Okay. So you multiply by the power of 10
Yes.
based on the number of decimals, right?
Yes.
So if it was only 2 repeating decimals, it would be 10 to the second, which is 100.
I guess you could say that however many repeating decimals you have, that's how many zeros you put.
Okay, so think about a way to write that down in your notes so when you come back to it, like a test or quiz, if you need some help in remembering. How would you write that? Multiplied by, I like to say power of 10 because 100 is 10 to the third. And that means there's 3 repeating decimals. The power matches the number of repeating decimals, right? 10 to the fourth would be 10,000.
Yes.
If there's 4 repeating decimals.
Yes.
That makes sense. Okay? So maybe we can say multiply by a power of 10 that matches the number, or the power matches the number of repeating decimals. Okay. Then what did you do?
Then you subtracted the original equation from step 1.
So make sure you write that next to the step. Put that in words, subtract the original equation.
And you're also subtracting the repeatingness.
So I should put, I should put
And it makes it no longer
equation
repetitive.
to get rid of the repeating decimal.
So it's no longer repetitive.
Okay. Then what?
Solve for x.
So we're going to actually do the subtraction, and we get this
6,148.
Eight, and then we're just going to take that and solve for x.
Yeah.
Right? So I end up with this. 6, 1, 4, 8. Okay? And then you can simplify that, but we're not going to worry about that right now. You get up 6 and something over 999, and maybe that simplifies. Even though I said that why I said it's about 6 or something else. Because this is really close to 1,000, right?
Yeah.
How many thousands are there in here? There's about 6, right? Yeah. So we'll have that. But right now we're not going to worry about simplifying that. Okay? So does that make sense? So now you know how to change a repeating decimal into a fraction. And that way you can tell if it's, you can kind of see that this is kind of proving that those repeating decimals are rational numbers, aren't they? Because I can change them into a fraction. We have to figure out a way to get rid of that repeating decimal in that process. Okay? So we've got a few minutes to get through the next section. A little bit. What did we learn? And we just basically went over that. And then we reasons for that. And I'm going to skip over this one. Basically, if you want to find a rational number between 1/11 and 72 repeating, 72 repeating, what do you think you should do?
You turn 0.72 repeating into a fraction.
Okay. Or you could turn 1/11 into a decimal and find something in between those two. Good. All right. Square root. Well, so we're going to talk about square root. But we already talked a little earlier about what does it mean to square a number. It means to take the number times itself. Okay? If I'm looking at that in this picture, we talked about the number 9 earlier, and so let's just use that. This side would be 3 as a square, and the square this side would also be 3, right? And its area would be 9. So the reason we say 3 squared with that little 2 there is because, why?
Oh, because you literally put a square in.
You literally found the area of a square, right?
Yeah.
Okay. So if it says 3 cubed,
That would be like 3 times 3 times 3.
right, and that would be like a cube, right? Mm-hmm. That would be length that's what's going to on a cube. Okay, that's why they use those words. Okay, and so for square rooting, like I said, we're going the opposite direction. Now, squaring, remember, the square like this only gives us the positive because of the length of the side, but you can also have -3 times -3, you get positive 9. So if I'm going to square root, like I said, you're going to go the opposite direction. Okay? So, in this case, if I give you 64, basically what I'm trying to find is, what I think squared is the length of the side of one of those squares. So what number times itself makes 64?
So you can 8 times 8.
Okay, so 8 times 8. This would be 8, and this would be 8. Okay? Now, one of the things that we need to keep in mind as we're doing this, again, if I take the square root, it could be, in the case of the square, it's a length, so I have to be positive 8, right? But it could be a -8 times -8, right? If I'm taking the square root.
So I just put it between this bracket thing.
You have to kind of, well, I'm going to show you something. When it's like this, and you're asked to take the square root of 64, when it's like this, they are assuming, you would have to assume that they want the positive square root.
Okay.
So that means that they want positive as the answer. Okay? If I said something like this, x squared equals 64, then you don't know which one it is, and you have to write both of them down.
Yeah.
Okay? That is, it's like the first one with the radical sign, then you assume it's a positive unless it has a negative out front. Okay? Now, this idea of having to find the length of the square, I'm going to clear this for a second. What if I said the area was 5 for this?
You'd have a decimal.
Okay, have a decimal. About how long do you think the side's going to be?
2.5.
2 and something, right?
Mm-hmm.
And if we try to figure it out, you know what? We're going to end up with a decimal that goes on forever that doesn't repeat. Okay? So oftentimes, unless we have what we call a perfect square, which is like that 64 where it comes out exactly at 8, or 4 would be a perfect square because I take the square of it, I get 2, right?
Yeah.
Or 2 times 2 is, you get that whole number answer.
So basically, numbers that don't have like a number times like multiplied by itself to get that number.
Yeah, they all have a number multiplied by itself, it's just that it's different decimal that goes on forever. So the ones that don't come out perfect are what we're looking at. The ones that come out perfect, that's what they're called perfect squares. Okay? The ones that don't come out perfect, those happen to be irrational numbers because they get that decimal that goes on forever. Okay? So like this right here is an irrational number because 3 is not a perfect square number. And 5 is an irrational number. All right? So one of the things that we're going to look at here is that if I'm adding and subtracting square roots, notice that I gave you an example. 2 square root 5 plus 7 square root 5 minus 3 square root 5 gives me 6 square root 5. So what did I do when I did this problem? Did I? So 2 square root 5 plus 7 square root 5 minus 3 square root 5 equals 6.
You have to because like all the squares are things that are just going to cancel out anyway.
It's
So you need to get that in there.
Ah,
yeah.
it's not like
It's kind of like a fraction, like because if you had like 2/3 minus 1/3, it's like the same thing because
Okay. Or if it's 2x plus 7x minus 3x.
yeah.
The x we didn't pay attention to x, we just did the coefficient, right?
Mm-hmm.
So it's the same kind of thing as square root. If the square roots are the same, like you said, then all I have to do is deal with the number in the front. Okay? Do you want to get that down? Just kind of make a note of that. That's the pattern. And then try the one on the bottom, see what you get. Whenever you guys told me this, you told me that when adding or subtracting, a like square root, kind of like, you have to, yeah, I mean, like denominators or like, yeah, like terms, right?
I came out with 4 square root 7 plus 2 square root 10.
Okay. What do you guys think about that?
Because you can't add those two fractions, so you might as well just combine or subtract like terms.
Yeah, it's kind of like saying 3x plus 4y minus 2y, right?
Mm-hmm.
You can't put the x's and y's together,
Yeah.
okay? So the square root, you can only add the square root, this are the same. So you're right. Look, I got this one, I got 3 square root 7, and I got 5 square root 7, so that makes
8 square root
8 square root 7 minus 4 square root 7 makes
4
4
square
square
root
root
7.
7. And then I can go back and do this one, 4 square root 10 minus 2 square root 10,
Is 2 square root
2
10.
square root 10.
So you end up with 4 square root 7 plus 2 square root 10.
Yeah. And make sure you make note that when we're adding or subtracting with like square root, you add the coefficient or the number. Yeah, I call it the coefficient. It's not officially that, but it helps you kind of understand it related to the algebra or the number in front of the square root. Okay. What about? You need a second to write that down, or?
Yeah.
This is one time I may have, you may have to kind of go back and pull up the recording and stuff forward to the point when you get results. So you get the point towards you got done, because then you get through this next little bit. Okay? So here's some examples of multiplying square roots. So in the first one, what did they do?
So it equals like,
Yeah, and then the square root signs at the top of it. What about the second one?
You multiplied both sides. You multiplied 2 with 3 and 2 with 5, so you ended up with 6 square root 10.
Uh-huh. Okay, you can see that? Look at the outside and the inside. Then what about the next one?
And
Yeah, same thing, except then when they got to here, they got a perfect square number. They got a perfect square number, and then they simplified it, didn't they? At the end. Okay? Excellent. The last little bit here. So basically, there's an issue here. Before we had square root of 16, but what happens if it's not a perfect square number? These aren't perfect square numbers. What did they do?
we put both.
Okay, they changed to multiplication. What number did they choose here? They didn't choose 2 and 6, did they? Why did they choose 4 and 3 instead of 2 and 6?
Because 4 has a square root.
Yeah, because 4 has a square root. Same thing with the one up above, right? The 9 has a square root. Okay? And so, when you split them apart, you run it backwards from what you just saw, you actually get the square root of those. Does that make sense? Okay? And so, now we can decide if something like that is a rational number. You look at it. And so then what they do is they simplified it to 16 times 2, 25 times 2, because these are perfect square numbers, right? Okay? And then over 2 makes 1. And now you can do that, and it comes out to be a fraction, so it is a rational number, even though it has a square root sign over the top of it. Okay? Make sense?
yeah.
All right, so you guys are done, and you get to go to you guys, the 3 and everybody else. much.